feel free to
Recording.
feel free to raise your hand and we'll get your name, phone number, email to get you signed up. Do we have any new people first time to the ASME Apollo meeting? Okay. Why don't you just say some name or who you with?
Jeffrey on the line.
My name is Drew Mehta. I'm a junior at UA studying mechanical engineering technology. Hello, my name is Christian. I am a sophomore at University of Houston Clear Lake. I'm studying mechanical engineering.
Hello everyone, my name is Neil. I'm also in UH Clear Lake studying mechanical engineering. Sophomore going to my
Hi, my name is Jose Niva. I'm also a student at UHCL, as well as studying mechanical engineering. Yes, Dr. Mannins are one of our chairs for the mechanical engineering school, so he was the one that informed us about this. This is a really cool opportunity to see the company and yeah, look forward to.
You guys just broke a record for the first, college group coming, so good job.
Yeah, let me go to the next slide.
No, I wanted to see all the names.
Oh, I'm sorry. You're right. We have to do our elections.
Yeah, this is the most important thing.
Is the most important
Can't wait
thing.
until we do this.
That's right.
All right, so my name is Mark Crawford. I work for Rotating Equipment Services, doing consulting for rotating equipment in the field, in the shop, and also helping in customer engineering. Lauren, right over here, he's the last year. Treasurer, the most important job, right here. Yeah, Phil Marino. Secretary, we got a volunteer, Jeff agreed to step up and learn the job of secretary.
Yay.
Program's chair, she's not here, Montano. And you say your last name? From Solar Turbines, so can't be here tonight. Member at large, also not here, is Edison Lamsel. He's the one that helped us put together the Zoom products and figuring out how to make it work. So I believe he's giving the presentation in
Yes.
September.
When we go to Cofundo's Pumps in September, that is his organization. So we'll go visit him.
And member at large is Ellen.
Yay.
Right there, she's been taking the secretary job for probably about 4 years.
Yeah, a few years.
She kept it straight and narrow in all the COVID opportunities, trying to learn how to do Zoom.
That's right.
Okay. So the first thing, anybody else wants to add their name to this list? Anybody?
All right.
All right, so no force volunteering tonight. All in favor of this, would you please say yay or nay?
Hi. Yay, yay.
Any no's that want to volunteer? Okay, good. So this, we'll send out everything with this because we got to have some officer activities to be
Yes.
done for planning next year. So we have a meeting scheduled to get final arrangements all done.
Right.
This is good proof. Respect, I speak to everyone in the same way, whether they are the garbage man or the president of the university. And we're not stopping. Very good way to carry on your business. You never know who's going to get ahead of you.
All right. All right. Well, in that case, I'm going to stop the share here. And I'm going to let Mike share. Okay. And I'm going to
All right.
You need to mute your mic and your speakers there.
All right, good deal. Well, thank you everybody here for coming out. It's always fun doing shop tour, especially seeing new faces and having a good sized group here. So appreciate it. Go on ahead. All right, so quick intro and agenda for what we're going to be going through today. Main topics are going to be how MHI, but really in general, kind of approaches compressors and steam turbine internal revamps and footprint replacements. Kind of talk what are the different options that you can go through as you're evaluating what you're doing in the plant, kind of the challenges and advantages that we see with doing footprint replacements, and then kind of the process for going about doing these things. We had planned to, at the end here, do the high-speed balance, call it theory, but the guy who's going to do this was Justin Fleming. Some of you guys may know. He had a emergency, so he was not able to attend. So unfortunately, we're not going to get into the high-speed balancing, but we'll make do with what we have here. All right, so we always throw this up just because Mitsubishi is a large company, but it's a large company of a bunch of different companies. There's actually no Mitsubishi head company. Us, the compressor group, we fall under the Mitsubishi Heavy. They've got multiple domains. So we've got the power group, Mitsubishi Power. You may run into those guys. They've got a facility here as well as in Japan. We've got, like every other big company, we've got government for defense and space systems. We've got our own company that does carbon capture. So they've got their own engineering division. So MHI is really who we fall under, and there's quite a few underneath us. All right, so what I think most of you saw these out there, but this is what we built. We got the API 617 type compressors, API 612 turbines, 617 Chapter 3 geared compressors. And as I mentioned, we've got a sister company, Mitsubishi Power, who also do gas turbines. So we do vertical split compressors, we do horizontal split, whatever it may be. So this is really our global footprint. So we've got obviously the factory here in Pearland, which we opened in 2015. Shortly after the big shale boom, we put a ton of machines out into the states all over, but mainly Gulf Coast. And so we had to have somewhere to service everything. So we opened this place up 2015. We've got our main factory back in Hiroshima, Japan, which is quite large if you compare it to what we have here. But yeah, so we've got about 850 people there sitting in Japan on the factory side, as well as engineering throughout the plant. We've got in London, we've got an outfit for sales, marketing. We've also got down in Brazil, we've got folks calling on people down in South America, and other entities in Korea, it's Saudi Arabia, and then we've also got something in Russia. So we're vertically integrated in the sense that from start to finish, we've really got control of our own, really our own destiny. But so the key thing to point out here is MHI Group has its own foundry for all the MHI group companies, they use single foundry that's in Kobe. So we'll get into something a little bit later, but that's kind of the key thing to take from this. But moving in throughout the whole process of building a machine from the first casting through the machining, assembling, testing, all of that's done under our own control.
We like to highlight that because it's a big differentiator between us and our competitors, where most have taken the methodology to start outsourcing a lot of the, their large castings, et cetera. We've been one of the few OEMs to really hold on to that. Plays into today's discussion because it does give us some flexibility when you're talking replacement of equipment.
Rotor forgings as well, just the casings.
Mainly casings, but we do get from our own company, we will get some of the sourcings for the rotors, yeah.
So you have forging capacity too.
Sorry, go back real quick. I guess one of the things to point out, you all saw, we've got a test stand here. We've got 1/2. Japan's got 19 of these things. This one here that's pictured is what we call a mega test stand for these large ethylene trains, which you'll see down here when they do the performance or mechanical runs. All right. Yeah, we've gone through this, these two here. You saw everything. Kind of just capacity for what we do here. New unit packaging, you saw the test stand. We can do manufacturing on stationary and rotating parts, whether it be steam turbine, whether it be compressor. We're doing repairs, we're doing overhauls on machines, TTV overhauls. We've got welding capabilities for pipe, as well as repairing the casings and things like that, or the shafts, whatever it may be.
It's any make of trip round well?
For sure our own, but if it, a gimbal valve comes over here, then yeah, we'll take a look at it too.
Yeah, we've overhauled 1 or 2 gimbals now. It's important to point out, right? The Mitsubishi TTV design is quite similar to a gimbal TTV.
Did you have an overspeed?
Yeah, so we had impeller overspeed, we had low speed, and we had high speed balance, but above ground high speed balance. And then, of course, storage was over here for all the big rotors. All right, so as I mentioned, 2012 was a big boom for shale gas, and that's when a lot of these big orders came out. So the growth was, call it exponential from that time for when we put in new machines. So 2012 to this day, we put in over 200 machines out in the field, steamers and compressors. This is just in North America. So
Mostly pipeline?
it's ethylene, ammonia, LNG. Those are the big markets we get in. Pipelines, certain manufacturers got a pretty good grip on the pipeline.
Yeah, I don't think we've got the slide in here, but generally speaking, biggest contributor to our business is ethylene and petrochemical. It accounts for probably around 40% of our market on any given year. The next largest chunk is in ammonia and methanol, traditionally for fertilizer. Now we're seeing a shift for transporting hydrogen, but ammonia probably accounts for another 20% of our business. Then the remaining, 40% is a combination of upstream, midstream, and other downstream applications.
So kind of a good segue. So for revamps, internal revamps, and footprint replacements, the main markets that we're getting involved in are ammonia and urea, methanol, ethylene, little bit here and there on nitric acid, and upstream. We consider LNG upstream. So focus today will be more on the left side though. So we'll have customers that'll go in and put 1,000 KTA ethylene plant, and then 5 years, 10 years later, they want to go put another couple hundred KTA. And so they come to us to do these studies, we do internal revamps, or we do footprint replacement, whatever it may be. So they kind of do a staggered procedure for making larger and more capacity.
Yeah, especially, today it's a good topic of discussion in ammonia in particular. If you watch ammonia pricing, it's actually through the roof right now. So you can make a relatively small capital investment to debottleneck a facility by either revamping or replacing your turbo machinery and get immediate return, call it 25 to 50% capacity expansion. Of course, depending on what other bottlenecks you have, but yeah, true.
Yeah, so this is our install reference for revamps and replacements globally. So you'll see the yellow boxes are ones where we've gone and ripped out others' machines and put our own in. That's almost 300. And the ones that we've gone and revamped or footprint replaced of our own machines, it's north of 400 machines. So we're talking 700 plus machines around the world that we've done this type of process.
Yeah, and one important thing to point out of these, references you see for replacement, fell asleep. Of those, 400 plus machines you see for replacement, a strong majority of those is actually replacing other OEMs machines. So getting in there and figuring out how to make the footprint work within a set of constraints driven by another OEM's machines. What happened here, Mike?
This was happening earlier, but they quit.
Are you back?
You still have us on there? Okay.
Some connection loose or something.
Yeah.
Is it the Zoom or is it the TV?
No, it's TV. This was happening earlier. Sorry about that, guys.
All right. Some connection loose on the.
Yeah.
All right, well, look and read fast, and we'll keep working along. So before we get into the details of when you may pursue a replacement of a machine versus a revamp, because both have their time and place, we're going to highlight there was several major, call it replacement and debottleneck projects in the lower 48 of the U.S. in the last year. Two of the largest we can share with you today, which we were successful in capturing. This is public information. There's a ammonia plant in Iowa where we're pulling out 2 existing turbines and 4 existing compressors. It's an old M.W. Kellogg design ammonia plant for those who may be familiar. Unique thing about that project is it's if you've ever worked in any of those ammonia facilities, it's what they call a topping turbine configuration. So you have a back pressure turbine plus a condensing turbine to get the power you need for that high-speed syngas train. We're actually pulling that out and putting in a new single body extraction type turbine in place there. So pretty monumental shift for those M.W. Kellogg designs. But the reason we highlight it is because we're able to do so without disturbing the existing footprint and with minimal impact to their piping. And they're debottlenecking that ammonia facility by about 15 to 20%. So they'll have an immediate capacity increase once they go through their turnaround this summer.
What's the ton?
Sorry?
What tonnage are you going to?
So this plant's going up to about 1,300 tons per day. So they've gone through those plants were originally designed around 600 tons per day. So they've been debottlenecked several times since the 60s. But yeah, in this case in particular, the turbo machinery was truly at its max threshold. The casings couldn't handle anymore. So the other project and another, the two biggest markets for debottlenecking through revamp or footprint replacement are really ammonia and petrochemicals. So the other one, which we showed on the right here, if you could see it at all, is a PDH plant here in Houston. Another example where we're pulling out another OEM's piece of equipment. And in this case, one of the larger machines, we're actually keeping the existing compressor. They just need more power out of their steam turbine. So we're actually not just replacing the existing turbine, but mating up with another OEM's driven compressor there.
So you're replacing with the same technology with the interior gear compressor, or from what the previous?
Yeah, more or less the same type of technology. Just I would say with modern manufactured components and added capacity in the existing footprint. So, right, your most monumental constraint you have when you're replacing a machine is the civil structure and foundation around that machine. So that's the biggest constraint you're working with. And in ammonia and petrochemical applications, most of those are configured to be mezzanine mounted with down nozzle orientations. And so you've got an opening in a preset footprint that you're constrained to. Well, you can imagine if I'm debottlenecking my compressor 25%, that machine is physically growing in size. Your bearing span is physically growing. So now you've got larger nozzle diameters you're trying to fit within a preset foundation opening. So that's the biggest challenge. So it's more or less the same technology, but with the twist on component modernization.
Maybe take a quick tech break if you don't mind.
See, what's the timing of either of those two projects we're talking about, with the ammonia first, and the PDH unit?
They're going in, so the ammonia will be installed this summer, and the PDH one is being installed Q1 next year.
Sorry about the guys on the other side, but I think you're going to end up having to look from just this. All right. How are you?
See, there was a question.
That was from earlier. Mike, if you're ready, you can start sharing.
You'll get the gist. All right, so for doing some sort of call it plant expansion, there's things that you're going to look at, right? You're going to look at how you're going to do it with your process, and there's more than just the turbomachinery, but you're going to have to look at what are your restrictions mechanically. What are you going to have for your plant turnaround schedule? How long do you have in case you're going to be doing some sort of revamp? These are the kind of things you got to consider whenever you're going to be doing some sort of expansion at the plant. So we've kind of broken it down for turbomachinery into 4 kind of categories. You can either just have some sort of process adjustment, get some sort of expansion out of the plant. You can do a internal revamp. You can do a footprint replacement, or you can just buy a whole new train and set it wherever it may be nearby the existing train. So that's kind of what we'll get into here for internal revamps and footprint replacement, kind of how we view that whole process.
How long does it take from the time you get an RFQ and have the contract to the time you have your finished product?
So
Kind of an average.
yeah, I'd say call it anywhere from 14 to 18, 20 months. It just depends how long the process study is going on and they finalize their stuff. But one of the things that Steve will get into is kind of how the process works, where we go out, we do a site walk, we take measurements, and if possible, look at existing drawings, things like that. And so that whole process, depending on, site availability, can take a little bit of time.
So roughly less than 2 years.
Yeah, I'd say so. As long as the customer's willing to move, yeah.
Sometimes.
Well, no comment. So if you're going to do some sort of process adjustment, you can do a suction pressure change. You can, if you've got a variable speed machine, you can speed it up. You can also change some of your steam conditions, but there's limitations that come along with that. So you've got existing casing design pressure limitations. You've got max continuous speed. So every compressor is going to have MCS, and so going beyond there is not recommended. And then you've also got limitations on your driver for the output power. So if you're going to do an internal revamp, we see you can get somewhere in the range of 10 to 25% additional capacity, just replacing internal elements, whether it be diaphragms and the rotor. But you've also got limitations here. You've got the bearing span, it's already fixed. You've got an existing machine, right? So you've also got your inner casing diameter. You can't grow beyond what you've already got. So that's really the limitations we see for internal. Now, footprint replacement, you can throw a brand new machine in here, whether it be a compressor or turbine, you can get some additional capacity. But a couple of things you got to look at is you're looking at your foundation size, looking at your existing piping. A lot of operators aren't going to want to be moving their piping that's already there, or their steel or civil work. When you start introducing those kind of things, it's a brand new project. It's very, very capital intensive. And so you have to be very cognizant of those type of things whenever you're doing a footprint replacement study. And then lastly, of course, you can do the new parallel train, which there's really no limitations with the exception of plot layout. If you've got the additional space and you got a limited checkbook, then you can do that. So we'll try to focus on 2 and 3 here. Jump in.
Yeah. So when you're weighing whether or not you're going to pursue your capacity increase or process adjustment via revamp or a complete footprint replacement, a lot of the times the discussion quickly goes to financials, right? And if that's strictly what you're focused on, an internal revamp is going to beat out a footprint replacement every single time. There's no doubt about that. They can't compete. But the key is evaluating what are your technical risks associated with pursuing that revamp. I go back to the reference you gave, that fertilizer plant that's going to about 1,300 tons per day. That had already gone through 3 or 4 bottlenecks over its life. So they were starting to push some mechanical limitations of equipment. A lot of times where we see that is in these older steam turbine driven applications. So focus of this slide here is what are those risks? So Commonly, the OEM of the original equipment is going to promote an internal revamp for CapEx reasons. However, in doing so, you're inherently running into mechanical limitations in terms of nozzle diameters, what your pressure losses are going to be, resulting in from increased nozzle velocity in those fixed diameters. We like to say that on a very generic level, that will result in pretty much a 3% reduction in efficiency of the machine. So that's one thing to be aware of, as opposed to a replacement where you can come in and you can really optimize around your new operating point. So that's one of the risks you run into when continuously debottlenecking through a revamp. There's other, performance related risks you need to be aware of, primarily caused by higher velocities at your fixed flanges. You're going to run into valving limitations in your throttle valve, governor valve, etc. But then one of the more important things is you're really starting to narrow in your operating map because your casing capacity is fixed. So oftentimes you go through this revamp, and then 3-4 years later in your next turnaround, you want to squeeze more out of it, and a footprint replacement becomes inevitable. There's other mechanical risks to be aware of. So you're having increased steam conditions that may not be suitable for the materials you have selected. So things like that you should be cognizant of if you're going to look at a revamp as opposed to a replacement of the machine. We like to show this image here when we're talking about footprint replacements. Go back to what we mentioned early on in the presentation about having our vertical integrated manufacturing philosophy, where we still have our our raw material coming from providers that are in-house Mitsubishi Group companies. It allows us to do some really flexible and unique things when it comes to casing design of the machine itself. So where you'll see a lot of OEMs today have standardized on more fixed frame designs, you go up from frame X to frame Y, and you've got fixed nozzle locations, fixed compressor or turbine diameter for that matter. That's not how we operate. So Mitsubishi as a company, we opt for what we call flexible frame design. So each casing is really sized for its proper application. And then, with the agreements, flexibility we have with our in-house material providers, we can get pretty unique to work within existing foundations. So this is a real example you're seeing highlighted on the screen, a debottleneck of a cracked gas train in ethylene service, where the 3 casings got physically larger. But again, this existing foundation, this is preset. This is something that can't be changed during a turnaround. So we actually, configured the nozzles to span the existing openings and work within those limitations. So again, just a visual representation of some of the unique things we can do. So biggest question we get a lot is, okay, your machine's getting larger. Yes, you don't want to touch the foundation, but what am I doing with the base plate that's got that fixed in place? There's 2 ways you can approach it. First and foremost, our goal is always going to be to try and reuse the existing base plate. Why do we do that? For anyone who's been up on a compressor deck, very well, there's oil flying around that can leave the quality of the concrete foundation in question. And getting into a turnaround, chipping out a base plate, trying to chip existing grout opens you up to a whole new can of risk that we generally try to avoid. So in any footprint replacement we're pursuing, we're going to try and make the best effort we can to reuse the existing base plate. One of the ways we do that is through a modification of base plate, a procedure in which we gas cut the existing pedestals. We'll bring in a new pedestal is in. Again, we're moving the pedestals because oftentimes if you're debottlenecking 25+%, your casing is physically getting larger, your bearing span's growing, so the existing pedestals simply don't work from a rotor dynamic perspective. So we'll gas cut them, get in there, new pedestals on. This is something our field service crews here are very well versed in. And the next slide again is just elaborating more on that process. So now option 2, if that does not work, because sometimes it does not, go ahead to the next slide, is replacing the existing base plate with a new base plate. So if you have to, you can get in there. You can remove the existing base plate, chip out the grout that's currently in place. Our first step will be to try and match all the existing foundation holes. That is not always possible. In case where it's not possible, so we have to add some new foundation holes, we'll do a chemical bolt in place to get in there and meet the new requirements of the bolt locations. So we've got experience with both. You know, the project I referenced early on, that fertilizer plant, there's 2 trains we're working on, and we were actually deploying both approaches. So one of the machines, we're actually pulling the base plate out, chipping the grout, laying a new base plate. The other, we're modifying the base plate and putting it in place. The key is we do have experience doing both of these methodologies within, you know, say a 45-day more or less turnaround window. So it is possible. So someone asked the question, I think came from over here, on timeline for getting some of this stuff done. So I think your question may have been around, you know, once the equipment is ordered, how long does it take to finish design, fabricate? So yeah, that depending on the type of arrangement you have, let's say it's a small motor driven train, that's going to be more around today, 14, 15-ish months. A large turbine driven application, that's where you're going to be pushing that 18-month time frame. That's from actual order placement. What we're laying out here is what happens before that. What happens, you know, when it's an idea at the dinner table that, hey, we want to debottleneck this plant by 25%. So the first is we need to understand what the existing process conditions are, and then what the target, you know, future conditions are. So with that, we'll take a look and say, okay, this is the type of machine you need. But to do so and figure out what constraints we need to work with, and we need to have a set of drawings from the owner, what exists there today. Primarily, you know, GA, foundation drawing, the existing data sheets if they're able to share, and then any supporting auxiliary equipment. From there, we'll produce a technical report with typically 1 to 2 options for replacing or revamping for that matter. Then the next big step, and this is key, is to go actually conduct a site survey. So these site surveys can vary. Sometimes we'll get out there and we'll take some very simple measurements using just, you know, tape measure or laser measuring tool, verify some of the things we need on the old drawing. Or we go to the extreme and we actually bring out laser scanning technology to create a point cloud, you know, walkthrough model of the machine. That's more rare, but is absolutely, you know, helpful if someone's willing to pursue that service. Again, while doing so, we try to keep minimal impact to all the surrounding auxiliaries, lube oil, surface condenser, if it's turbine drive, seal oil or dry gas seal systems. We'll try and reuse as much of that as possible. Sometimes you need to replace it. Sometimes you're just making component level modification, swapping out an oil pump, something like that. Kind of once we align on that, that's typically when the customer will go through their formal RFQ process. So let's say 1 through 4, you know, sometimes that can span multiple years. I can tell you, you know, we've got one ethylene plant in particular we've been studying a debottleneck on since the day we put in the new machines. So that's been going on over a 4-year period, right? That's a massive debottleneck, so that takes a lot of time. But more importantly, it takes a lot of time for them to convince their management to, you know, pursue those funds, and it takes an environment with whatever product they're producing to justify it. Once a formal RFQ is issued, depending on how fast they want to go, this is typically anywhere from 6 months to a year. All right, so, you know, we've talked a lot about footprint replacements and what the benefits are technically, but what are some of the other, you know, less quantifiable benefits? And the big one, which, you know, we find a lot of customers focus on footprint replacements for revamps on, is when you're doing a new casing, it allows you the ability to validate that quoted performance before you get to the field. Because you've got that casing available, you've seen our test stand here, we showed pictures of our test stand in Hiroshima. It allows you to conduct, be it a ASME PTC 10 type 2 performance test or a mechanical run test on a turbine. It allows you to validate that performance before your machine ships to the field. as opposed to a revamping approach where it's all theoretical until you get that machine in sight and you send gas back to it after your turnaround's complete. So I'd say this first check mark we're showing, that's probably number one reason certain major customers always opt to pursue a replacement over a revamp. It's just it's a matter of what level of risk are you willing to take at sacrifice of CapEx. Mechanical integrity, same thing, run test versus, as opposed to performance test. Other major thing is you're reducing the amount of in turnaround work you're doing. So that core machine shows up typically 2 to 3 months before turnaround. You're doing any prep work, dry gas seal installation, etc., before you're lifting up and dropping it on the mezzanine. Other things we already talked through, design flexibility, etc. So last slide we want to bring it home with, all this sounds great. I already mentioned it, but none of it is good if you need to bring plant down for, an unjustifiable amount of time. So the name of the game is trying to work all these types of replacements or revamps into a standard plan turnaround. So, and this is mechanical turnaround days that we're showing, the 40 to 45 day gap. This is the typical target. Of course, it varies depending on type of plant and what the overall scope at the, overhaul scope within the entire plant is. But generally speaking, this is where we need to work within. I'd say for the 45 days is your larger equipment. Think an ethylene crack gas train. The 30 days is more your smaller ammonia syngas type applications, where you can see that. But these are real days. This is an example of a real project. The two we showed earlier, two of those trains are sitting at 34 and 38 days target schedule right now. So take a moment to, with that, plug our field service team here that, kind of specializes in these activities and provide that type of planning as a service as well. So they'll sit down, spend weeks at the customer site with their planners and their turnaround management, laying out exactly step by step how this machine is going to go in within that turnaround.
Okay. What you got after this, Ellen? Okay.
The two different outages, one being revamp, one being the replacement. Which one is the most challenging? Sometimes you can have a drop in, sometimes you have case modification.
Yeah. So I would say both of them come with their challenges. Footprint replacement is challenging, that it's a lot of heavy equipment, right? So sometimes it also comes with piping modifications. Piping modification can be a big no-no for some folks during turnaround. So if that's one thing you're not willing to entertain, then that's kind of a bottleneck, if you will. The most challenging part of a revamp is not knowing what you're getting into. So some of these casings you're opening up, maybe the first time they've been opened up in 8 to 12 years. And so yes, you think you've got your plan set, exactly what you're going to go in and all, the new diaphragms, new rotor, everything's going to fit great because I got the drawings, and you open it up and it's a crack gas service, which is naturally a very dirty service, and you've got galling on the case or fouling on the case, and all of a sudden, hey, I actually do have to pull this case out for rework at the shop, and that's unplanned in turnaround work.
On the replacement work, how do you come up with warranty? You warranty only your equipment, but your parts are part of the bigger component. Yeah. So casing and piping and pumps and all that comes into play. How do you manage that warranty to the customer?
Yeah, we would just warrant our own equipment.
Your own equipment.
Yeah. Because it's
Some of those cases on those ammonia plants are 50 years old, I know.
at least, yeah, we would. Yeah, that's how that would work. We can, yeah. I mean, traditionally on new equipment, yes, but even on these, sometimes, they got 60-year-old, they got gauges out there and they're,
All pneumatic.
yeah. So that is a lot of the times some of the upgrades that they'll do. But that's a much deeper upgrade, right? Because then maybe you're integrating with your DCS or something like that, so. Yeah.
That's one of the biggest challenges with the old equipment, is the drawing quality is poor or mismanaged. And that's why that site survey is so key for us, is to go validate some of the things we're reading on the drawings. Because oftentimes things have been modified on those drawings, and a lot of those older drawings may not even be valid anymore. So.
Well, you got a photocopy of a photocopy of a photocopy. The legibility is gone.
Plus it's been changed.
Yeah, exactly.
Here, somebody's done something
Yep.
in the middle of the night.
Anything else?
Thank you, MHI, for hosting us. It was an excellent tour. I think some of the young potential engineers get to see what you get to work with in the future. So.
You guys.
Thank you guys for coming. We like to show off our facilities.
Thank you, Mark. Appreciate that.
Thank you for hosting. As I said, it's always a pleasure. I think you've done 2 or 3 of these over the last couple of years, and each one is something different.
Yeah.
That you introduce us to.
That's good. Glad to have you guys out.
If we ever pitch a repeat topic, yell at us. Me and Mike were like 2% last time.
Yeah. Well, I got one, just did a revamp in Port Arthur for TV.
Yeah, we did their propylene refrigeration machine.
Yeah.
It just went in maybe 6-7 weeks ago.
Yep. I know somebody that was on the project.
Okay.
Yeah.
All right, anybody professional in here? Come on up here and get one.
And if you need a PDH compressor.
That's right.
Scott.
Yeah.
Yeah.
Who else on this side? I think you do. You need one? Your what?
I was the chairman.
Oh, okay.
If you need some help, if you did a meeting, give me a call. And if I'm not busy,